questions am I to assume that everything is crystal clear, or that you just haven't had the time to go through them?
Sir, in
Okay, there were two
semi-direct
people speaking at the
product,
same time, so one by one. Okay.
yeah, yes, sir. So just a second.
Mhm. So this is becoming a bit of a pehle aap situation. So
Yes, sir.
go ahead.
So in semi-direct product,
Hmm.
we said that we need a automorphism group. So
You need
my
something which is at least isomorphic to a subset of the automorphism group, a subgroup of the automorphism group. Yes.
yeah, yes, sir. So uh, we didn't say like why did we need like how did we come to the intuition that we need the automorphism group?
Well, basically, if you look at the product rule, you had this rule, right? G alpha, G prime, alpha prime. So
Hmm.
what was the product like? The product was alpha and alpha prime combined among themselves, but G does not get
G
to
alpha.
directly.
Uh,
But that means that alpha G prime is something you should be able to do, right? That is the
yes, sir.
element alpha, which is the element from the second set, has to be able to act on G prime somehow and produce a new element from capital G. So if you are doing a semi-direct product between G and curly G, the elements of curly G must be such that they act on the elements of G prime, on capital G. Otherwise, this thing will not make any sense, right?
Mhm. Yes, sir.
So just like in our example, we had lambda alpha of the Poincaré group, we had this, right? Lambda 1 alpha 1, lambda 2 alpha 2 was lambda 1 lambda 2. And then instead of alpha 1 plus alpha 2, which is the standard group structure in the translation group, what you have is lambda 1 alpha 2, alpha 1 plus that, right? So instead of alpha 1 plus alpha 2, the lambda goes and acts on alpha first and then produces a new Bohr vector and adds, that gets added to alpha. So basically, here the Lorentz group has elements which could act on the translation group parameters, which is what is happening here.
So we look at the group composition rule first, and then we define the structure. Is that so? Or
Well, basically, it's a consistent thing, right? If you did not have an automorphism group, you would not be able to write down that product law.
yes, sir. Yeah.
It's a matter of consistency. And this here, the only word of warning that I would have for you here is that here in the standard Poincaré group notation, you write the Lorentz group element first and the translation after that. But here it's the translation group which corresponds to capital G, and the Lorentz group which corresponds to curly G. Okay, right? So
Yes,
the
sir.
only difference is that here the order is reversed. It's a standard way of writing things. That is a formal, usual way of writing semi-direct products. You write semi-direct product in this order. Unlike direct products, where basically you are taking direct product of two groups, it doesn't matter which one comes first, which one comes next. You end up with the same structure either way, right? Of course, what will happen is if instead of G1 cross G1 direct product G2, you did G2 direct product G1, the elements would of course be different, right? Because here the typical element will be small g1, g2. Here the typical element will be small g2, small g1. However, there's an obvious one-to-one correspondence between that which preserves group structure. So these two things are isomorphic. And there's the kind of reason why we don't bother distinguishing between isomorphic groups. It's obvious that G1 direct product G2 and G2 direct product G1 are one and the same. There is really no difference between them except in the formal way of writing down the elements. When you list them, they look different at first sight. Okay. On the other hand, when you're forming semi-direct products, the two groups are not at the same stature. They are different. That is, one has to be able to act on the other. Okay. So here the order matters. While you can form this semi-direct product, most often you will not be able to make sense of this. Unless it so happens that that capital G also can act on curly G somehow. Okay?
Yes, sir. Thank you.
Okay. Any further questions? If not, let me try repeating in a way what I discussed in the last class. I'm sure last class's discussion on molecular vibrations was not very clear. So I hope today I will make it clearer. Again, I will not tell you all the details of the calculation for the simple reason that the steps involved there or the mathematical techniques we need on the way are essentially ones we are going to pick up over the next few lectures. That is, in the details of the study of group representation theory. But what I wanted to tell you about is this. We have already started group representation theory, so I hope everybody has seen the first lecture. But that's sort of just the beginning. There's a lot more to come there. So let me just remind you that we were trying to say something like this. You have an equilateral triangle-shaped molecule, that is your 3 atoms at 3 corners. And you wanted to talk about molecular vibrations, small vibrations of this molecule, as long as the vibrations were in the plane. We are sort of pretending at this moment that we are in a 2-dimensional world and everything can only move in 2 dimensions. Okay? And so we started out by saying what kind of molecular displacements can you have? Or how would you describe the molecular displacements? What kind of space would the molecular displacements inhabit? And the answer is simple. Each of the 3 atoms at the 3 corners, they would get displaced. And as long as we are talking about small oscillations, it's pretty easy to figure out, even if the atoms were identical, which atom was where. That is, once this molecule sort of distorts and becomes something like this, let's say, that's an exaggerated displacement because then it will no longer be sort of a small oscillation. But if you pretend that this is what the small oscillation is like, I just exaggerated the drawing so that I can show you the displacements, then it's easy to see that I can easily identify that this is the atom which went here, right? And not this one which went here. This one went here, this one went here. So we can describe the motion by specifying how each one of the atoms are getting displaced. Like this corner, the atom in this corner is getting displaced by this much, atom in this corner is getting displaced by this much, atom in this corner is getting displaced by this much. And to describe the displacement of each of the atoms, we could of course just draw just use basis vectors here, 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 here and here. So 6 basis vectors, E1, E2, E3, E4, E5 and E6. And the general displaced configuration would be essentially given by x1 E1 plus x2 E2 plus x3 E3 plus x4 E4 plus x5 E5 plus x6 E6. But you know that x1 x2 essentially talk about the displacement of this atom, x3 x4 about this atom, and x5 x6 about this atom. Okay, so we have a 6-dimensional vector space. Well, actually we had done a bit more of advanced geometry. We would have known that this is really a vector bundle. So although I don't really want to use such a advanced terminology here, let me just point out that it's really not that strange a thing. It's saying that you actually have 3 different vector spaces here. You have one vector space tied down to this corner, another one tied down to this corner, another one tied down to this corner. And these 3 vector spaces are bundled together to form an effective 6-dimensional vector space. Am I making sense here? The nomenclature vector bundle is just one special name out of lots of different bundles that we talk about in advanced geometry and geometrical physics. But for the time being, these are just three vector spaces at stuck to three corners of the atom, of the molecule. And this together gives us this six-dimensional vector space. Okay. Now the basic idea, the basic physics here is something like this. Let me just say that suppose during oscillations at a particular instant of time, the things were frozen like this. I've taken a snapshot and this is the displacement that you see. Okay. Now, suppose that instead of this, let's just say that I imagine a configuration where everything has been reflected about this line. Okay, maybe I will just draw this line a bit differently. Okay. This one is maybe like this. Now, if I reflect this whole configuration at this instant, what will happen? I will get another set of displacements, which is this vector. I'm going to draw the new displacements in blue. This vector is going to now point like this. So this one will not point like this. This one will actually point here, right? Because under the reflection, this atom as a whole has moved here and this displacement has been carried here. And this one will move like this. Okay. Now, the important physical point is as follows. If you forget about the blue lines for the time being, just focus on the red line. That is the displacement of the three particles, three atoms at a given instant. Now imagine that we have allowed the system to move. That is, we were talking about a snapshot at this instant, and after that, let's look at the whole movie. What's going to happen? This bunch is going to move like this. So move somehow. Anyway, it will move in a pretty complicated fashion in general. Unless you have been very clever to set up the situation just right, the motion is going to be pretty complicated. Okay, but you can get a whole movie of displacements which will tell you how these particles travel, and so on, and they will oscillate back and forth in small vibrations, but in a complicated fashion, because typically it will not be one single frequency, but a superposition of lots of different frequencies, right? Unless you have been clever enough just to excite one particular normal mode, what you're going to get is a combination of lots of frequencies. Okay. However, the important question is, if instead of starting with this red displacement, I started with the blue displacements, what would happen? I will get another set of motion, right? With the red displacement, maybe it's going to the things are going to travel like this. With the blue one, how will they travel? Can you figure out how the atoms will move if this were the initial configuration? Given, let's say somehow you have the movie of how the atoms will move if the red ones were the initial configuration. Then can you tell me how the atoms will move? The blue ones were the initial configuration.
In the exact opposite direction, like we are moving anti-clockwise now, so the blue ones will move clockwise.
Well, that is not really that simple. It's basically, or actually, there's a simpler way to put what you said. I'm guessing that you mean the right thing. In this case, it will move like this. Let's say. So will it be anti-clockwise? Actually, it will move like this. It will move clockwise. Yeah. If the red ones move like this, blue ones will move like this. Okay. But the important thing is, if you were to take the movie of the red ones displacements and just reflect the movie along this line, the movie that you will get is exactly the movie which the blue ones will trace out. Right? Is that okay? The initial configuration that I have got for the blue displacements is exactly what you get by reflecting along this medial line the red displacements, right? And if you let the thing run, that is, if you allow the whole movie to unfold, the blue ones will actually move exactly in a mirror image under this reflection of the red ones' movements. Okay, so when you're saying clockwise and counterclockwise, actually it's a bit simplistic because you're talking of the displacement of this one alone. Let's say here, let's say the red one will move like this. What the blue ones will do is this blue one, not this one, will move like this in a mirror image of this one. And whereas if this red one moved like this, okay, I've painted myself into a corner by drawing too complicated drawing. But if that was going to happen, this is going to move like this somewhere. That is, the whole thing will be a mirror image of what you started with. Why? Because you should not be able to tell whether you have done that reflection or not. Whether you actually did the reflection or not, the motion would be indistinguishable from an actually reflected motion and the original thing, because the reflection is a symmetry of the system. Is this much clear?
Yes, sir.
Okay. So one immediate consequence of this, and this is one point which I guess I forgot to mention because I thought it was obvious the last class, which is this. Suppose I have this set of equations, m omega square, or let's look at the original differential equations. Oops. This was the equation that we had, right? Minus f zeta, where f is, okay, I wrote it k last time, I guess. So let's use the same language. So this is a spring constant matrix, which is relevant for small oscillations. And this is the equation that you will have for the original one. Now, suppose I do some kind of rotation or reflection, some symmetry operation on the system, which leaves the system intact. Then what will happen? If I did any transformation, xi becomes r xi. Then, since r is a fixed quantity, it doesn't change with time, the equation will change to this. Okay? So the rotated coordinates will obey an equation like this. Right? And then that means that if the original coordinates, so these are really, okay, let's say xi is what you get from the rotated coordinates. Let's call this xi tilde. Let's distinguish them properly. So what you are getting is minus r inverse kr xi tilde, right? So the upshot of all this is, if you were to carry out some kind of transformation on the coordinates, then the spring constant matrix should change by this rule. It should become r inverse kr. That should not come as a surprise. That's exactly what happens whenever you change your physical basis. Right? If you're using different coordinates, you're essentially changing your basis at the same time. And that is exactly what is described here. But if this were a symmetry of the system, that is, you should not be able to distinguish between the motion, whether you were using xi or xi tilde. If r were a symmetry of your molecule, so that whether you actually carried out r or not should not be distinguishable from the physical behavior of the system, then what would you expect this to be?
Minus k.
You mean minus k meaning the whole thing becomes plus k, or you mean this will become just k?
This will become just k.
Exactly. You expect the same equation if you have a symmetry in such a way that you should not be able to distinguish between xi and xi tilde. As far as observations are concerned, the spring constant matrix should stay the same. But what does that tell you about k and r? It tells you that r inverse kr must be equal to k, which means k must commute with r. So that is the first starting point. That is, if you have a symmetry operation which leaves your physical system indistinguishable from what it was before the symmetry operation, then the spring constant matrix, which is a relevant physical quantity in this particular problem, must commute with the matrix which describes that symmetry operation. Clear?
So here R should correspond to a reflection about this A, I mean this
Here
axis.
R is the, okay, here in my particular example, R corresponds to the reflection about this line, but it could correspond to any one of the other symmetry operations possible. It could be, so there's not one relation. K does not commute with one R, K actually commutes with 6 R's here. Right? Because
Yes,
there are
sir.
6 operations, 6 symmetry operations. One of them, of course, is trivially the identity, but still, it's a symmetry operation. So you have 6 symmetry operations, K commutes with each one of them. Okay? So that is the information which the physics of the system gives you, that the force constant matrix must commute with all the matrices which are describing the displacements under the symmetries. Okay? Not arbitrary displacements, but those which are symmetries of the system. For them, K must commute with R. Okay? So basically what we are talking about, if you've seen the last lecture, you would know that every symmetry operation can have a corresponding matrix representation. And what we are really saying here is you have 6 such matrices in your matrix representation, RE, RA, RB, RC, RD, RF, one for each group element. And each of these matrices, which will be 6 by 6 matrices here, because we are talking about a 6-dimensional vector space on which my transformation acts, K must commute with each one of the 6 matrices. Okay? So is everybody clear about that? That is the important physical point. So K actually does not commute with a single R, it commutes with all these RGs. Okay, this is a particularly simple physical situation. In other physical situations, it might so happen that what you're using to describe the physics may not commute with all the matrix elements, matrices representing the group elements, but might have well-defined and nice, say, transformation properties under those particular operations. We will see them as we talk of more and more physical applications. But this is a particularly simple situation where the demand that if you were to reflect your molecule or rotate your molecule through one of those symmetry operations, you should not be tell from any physical observation whether you have done it or not. Essentially tells you that this spin constant matrix K has to commute with all these R's. Is this okay with everybody?
Yes, sir.
Okay, is there any question about this? Somebody was speaking, I couldn't hear that.
Sir, why is
Sorry. Can you, are you still speaking? Because I just heard why is. Am I still here? Yeah, I'm still here. Yes? Can everybody hear me clearly?
Yes, sir.
Yes, sir. It could
Okay,
be a network problem at his side.
yeah. Okay, why are there 6 matrices? Okay. 6 matrices simply because we have 6 symmetry operations. I'm talking of this equilateral triangle in particular. Of course, for other physical systems, you will have different symmetry groups. You will have different number of matrices. Okay. The 6 here is simply because my system, which is the equilateral triangle, has 6 symmetry operations, and so you have one such representative matrix for each one of those. And just like K has to commute with the matrix which represents a reflection about the medial line, it has to commute with all those other ones as well. The same argument can be repeated. If instead of reflecting along this line, I had rotated the whole system, then I would have produced some other, say this vector would have gone here and pointed like this. This vector would have come here, pointed somewhat like this. This vector would have gone here, pointed somewhat like this. And then the motion of that motion starting from that would be a rotated version of the motion starting from the red displacements. So you have one such R for each one of the symmetry operations. So K has to commute with every one of them. Okay. Now remember, our aim basically is to find the eigenvalues and eigenfunctions of K, right? Those are my normal frequencies and normal coordinates. Because that is what we are aiming at. It should be great news that I have found 6 matrices which commute with K, right? And if you think about how you use this in quantum mechanics, if you have an operator whose eigenvalues you want to find out, and you have found out a bunch of matrices, maybe simpler matrices which you know more about, which commute, or simpler operators in quantum mechanics, each which commute among each other and commutes with this matrix or this operator, then it makes it very easy for you to choose a basis in which this particular operator can be diagonalized, right? That's exactly what you did when you looked at complete set of commuting observables and stuff like that. Say when you had this system in a central potential, what made life very easy for you is that L square and Lz. In fact, L square, Lx, Ly, Lz, all of them commute with H. So what you did was, since L square, Lx, Ly, Lz, all of them did not commute among each other, you started with the best you had, that is L square and Lz commuting among each other, started with their eigenbasis, that is vectors or wave functions which are eigenstates of L square and Lz, and within that eigenspace looked for H's eigenvalues and eigenfunctions, and it became a much easier task. Is that clear to everybody? So what would you do here? You have got 6 matrices which each of which commute with K. So if they all commuted with each other, then life would be very, very nice. Then all you would say is, okay, let's find out their simultaneous eigenkets. And then K will be automatically all diagonalized the moment you do that. So basically, if you can find a basis in which the RE, RA, RB, RC, RD, and RF were all diagonal simultaneously, then it's pretty easy to see then K would also be diagonal in that basis. Being diagonal in the basis means what? Then it means that the basis vectors are the eigenvectors. And as I said in the last class, if you know the eigenvectors, finding out the eigenvalues is trivial. Okay? Finding out the eigenvalues ab initio is a complicated problem. You have to solve a 6th order equation in this case, because you have to find the eigenvalues of a 6 by 6 matrix. But in general, the eigenvalue determination problem is much more complicated. But given an eigenvector, finding out the eigenvalue is trivial, right? Now, what makes this program not so easy to use is simply the fact that these 6 matrices don't commute among each other, right? And what is very important is to realize that if A and B gives you some matrix element, I've forgotten which one AB is, either D or F. Let's say if AB were D, let's say if, then RA, RB must be RD, right? Because what does AB equal to D mean? It means that if you do B first and then do A, the result is the same as D. But RB is exactly what describes what B will do to these 6 basis vectors. So you do B first, the 6 basis vectors will change by RB will act on them. Then you do A, RA will act on the resulting vectors. So basically you are getting RB times RA acting in reverse order, because you always write the later acting vector first. So RA, RB acting on whatever vector you started with. So it must be RD. Okay?
Sir.
Yeah.
Sir, but shouldn't RE commute with all other matrices?
RE is the identity. It of course commutes with all the matrices.
Yes, so
When I say don't commute with each other, I don't mean none of them commute with each other.
Okay.
I mean all of them don't commute with each other. By the way, RE unfortunately gives although it commutes with everything, it doesn't really tell you much because RE is any vector can be RE's eigenvector, right?
Yes, sir.
So pinning down an RE eigenvector tells you nothing about the vector. Okay.
Yes,
The
sir.
whole point is, if I can pin down some of the eigenvectors, then what will happen is K will have to be within those eigenspaces, so you deal with smaller problems. RE unfortunately doesn't help. Every vector is an RE eigenvector, so knowing that K commutes with RE actually gives you no extra information about K. That knowing that K commutes with RA and RB, etc., actually does give you a lot of information. The only problem is that information is not immediately available right now, but let me just point out that if you could go to a basis in which RE, RA, RB, RC, whatever, all these six were all diagonal, then of course the matrices would simply look like this, right? They would look like six diagonal, possibly non-zero entries, and all the rest would be zero. And this would be the structure for all of them. All the RGs would have this structure, right? Now, notice that all these six matrices are actually diagonalizable. So you will always be able to find some basis or the other in which, say, RA looks like this. Okay? If your original basis choice did not do that, fine, you will always be able to find some other basis choice in which RA will be diagonal. But in that basis, RB will not be diagonal. Okay? Clear?
Sir,
So, yeah,
sir, I have a question regarding Poincare group.
we can come back to that later.
Okay. Okay.
Okay, let's remind me at the end of the class. I will come back to that. Okay, so what I was saying is, it would be lovely if we could diagonalize all of them, because then the common eigenbasis, the basis in which you're writing them all as a diagonal thing, that basis would be guaranteed to be also an eigenbasis for K, and K's eigenvalues can be read off just by looking at it. Okay. Things will not be that easy here, but the closest you can get to that is something like this. RA might end up looking somewhat like this. Well, not only RA, all the RGs, this is not possible. You can't do this for all the RGs. But it may be possible to do this for all the RGs, that you may be able to find a basis in which each of the R's have a structure like this: one 2x2 matrix along the diagonal, another 2x2 matrix along the diagonal, a 1x1 matrix, another 1x1 matrix. Okay. I'm not guaranteeing that this can be done in this particular case. I'm saying in principle, this should be possible. Okay. In fact, this is exactly, we are going to learn exactly how to see whether it's possible at all, and then how to carry out the change of basis in which, if it is possible, you will achieve this. Am I making sense now? Yes?
Yes, sir.
So,
Can you repeat the last part where you said you went from? You said you went from eigenkets.
Yeah,
Eigenkets.
demanding eigenstates or eigenvectors. Here, of course, these are not. You can call them kets just as well, right? Because kets are just vectors in a vector space. But these are just ordinary column vectors. Well, what we would have loved to have is eigenkets for all of the six vectors, simultaneous eigenkets, in which case all the six matrices would be diagonal together. But that would be inconsistent because RA-RB and RB-RA are not the same. These two, when you do these two successive reflections, AB and BA, you actually don't get the same rotation. Actually, you get the inverse of the other rotation.
Yes, sir.
Okay? So basically, this means that if your matrices should not really be all diagonal at the same time, because if they were, diagonal matrices always commute. So then RA-RB would have to be equal to RB-RA. So you can't have this. This is not possible. This would have been lovely, but this can't be achieved. The best you can achieve is something like this. You can choose a basis. So in such a way, instead of the original basis you chose, you could choose a basis in such a way that you will get a 2x2 block. That is under A, B, C, D, F, G. What does this 2x2 block really mean? It means that if my new basis vectors here were E1, E2, E3, E4, E5, E6, then this what is the structure telling you? It's telling you that when you apply, let's say this is the structure for RA, then what does this tell you? It tells you that when you apply RA, then E1 and E2 get mixed among each other. But the new E1 will not have any E3, E4, E5, E6 in it. Is that okay? Is that making sense?
Yes, yes.
Yes, sir.
Similarly, E3, E4 will mix among each other. But no E1, no E2, no E5, no E6 will come in. Right? Under
Yes.
action of RA, E4 will only transform into E4 times whatever this number is. Right? Nothing else. E5, sorry, not E4, E5. E5 will only transform into E5 times whatever this number is. And E6 will transform into only E6 times whatever this number is. Okay? So what we are saying is the space spanned by E1, E2. What is the span of E1, E2? If you remember your linear algebra, the span of E1, E2 is just all the linear combinations of E1 and E2. That's a subspace, of course, of your full space. Right? But
Yes.
what is this really telling you? It's telling you that when A acts, any linear combination of E1, E2 will stay a linear combination of E1, E2. Right? Take any vector in the span of E1, E2, it stays within the span of E1, E2, does not go outside because A is acting on it. Clear? Similarly, the span of E3, E4. So if this is the correct span of E1, E2 is invariant under RA. When I say, remember when you say a set is invariant, what you really mean is when RA acts on a vector in the set, you get a resulting vector in that set. You are not going outside that. Clear?
Yes, sir.
Okay. Similarly, span of E3, E4 is invariant. The one-dimensional subspaces spanned by E5 and E6 are also invariant. Okay. But are they invariant only under RA? No. We are claiming that they are invariant under the action of all the 6 group of symmetry operations. Okay. So span E1, E2, take any vector in that, apply the operation A on that, B on that, C on that, whatever. You end up with different vectors in every time, perhaps. But these different vectors are all within the span of E1 and E2. You are not going to mix up the others in this. Right? So basically what it is doing is it's breaking up your 6-dimensional space into smaller pieces. Smaller pieces which are all invariant under the action of the group symmetry elements. Okay? Is this much clear? So if we could find this, and we can actually find this, but I'm not telling you how to, but we will learn how to in the course of the next few lectures. But if you could do this, if you could actually find a new basis in which the matrices all become block diagonal with the same block diagonal structure, then what you have done is you have broken down your entire space into smaller subspaces each of which is invariant under the action of the symmetry elements, all the symmetry elements. So are there any, this is actually the most important notion of today's class. Not only that, it's actually going to be one of the most important notions in the application of group theory to any physical problem. So is this issue clear? If anybody has any confusion about this, speak up.
Sir, I have a doubt.
Yeah, go ahead.
So the block diagonal terms must be this 2 cross 2, or are we also allowing the 3 cross 3?
Okay, good point.
To be in?
Are we allowing 3 cross 3, 2 cross 2, etc., etc.? Well, this depends on the particular group you are talking about. Okay.
Okay.
These small blocks that you see, or rather the invariant subspaces, they carry representations of the group by themselves. In other words, you should realize that because RA, when it acts on E1, E2, it only gives you some combination of E1, E2, and so on, can simply forget about the rest of the space and just focus on what RA, RB, RC does to E1 and E2. And that will give you a two-dimensional representation, a 2x2 bunch of matrices. Okay. Now, what I'm saying here, I'm actually giving out a result which I have not discussed yet. But let me point out that what you're doing here is you're breaking up your entire space into smaller invariant subspaces. Okay. If you can do that, if your original vector space is such that under the action of your symmetry group, it breaks up into smaller invariant subspaces, then the representation that the original vector space gave you, I hope that terminology is clear to everybody. That was in the last lecture. That was the most important part of the last lecture. Given a vector space, what does it mean to say you have a representation on it? But the representation that you had on the 6-dimensional vector space is of a kind which is called reducible. So what you are talking about are reducible space. This is a reducible representation. The original 6D representation provided by the space spanned by that E1, E2, E3, the original E1, E2. Okay, sorry, I used E1, E2 there also, right? So maybe I'll use E1 bar, E2 bar here. The original vectors that I wrote down, okay, they furnished us a 6-dimensional representation, a bunch of 6x6 matrices. This happens to be a reducible representation because by changing your basis, not necessarily sticking to the original ones, but coming out with some new combination of vectors, I have been able to find that there are invariant subspaces where vectors in each subspace only mixes among themselves under all the symmetry operations. So such a representation is called reducible, something from which you can get smaller pieces like this. And if you can't get any smaller pieces, then that representation is called irreducible. And since irreducible representation is horribly difficult to pronounce, I find it horribly difficult to pronounce. I don't know about others. And I'm sure that is what everybody finds. And that is why it's almost universal that you call them irreps. That's short for irreducible representations. Okay. So what we are looking at here are irreducible representations of the original group. Of course, if it's a 1x1 representation, one vector transforming into itself, that is irreducible by definition, right? You can't go any lower than that. However, if you have a 4x4 representation, it may be reducible, may be irreducible. How would you know that? You would know that by essentially learning more group theory. That's what the rest of the group representation theory course is about, how to tell whether a representation given to you is reducible or not. If you're lucky enough to find the block diagonal structure, you know it is reducible because that's reduced already. But in most cases, you will not be so lucky to find a block diagonal structure off the bat, because the basis vectors you will start out with will not necessarily be the nicest possible basis vectors for the problem. Okay. Coming back to this question about can there be 3 by 3 that, or 4 by 4 or even 6 by 6? The answer is, at least for this particular group, S3, the largest irreducible representation is 2 by 2. That's an answer, that's a statement right now. I've not shown you how to prove this. In 5 or 6 classes, you should be able to prove it yourself. So, for this particular problem, having a 3 by 3 block would simply be a sign that you have not been able to diagonalize it properly. If you of course, you have a 3 by 3 block here, right? This one is a 3 by 3 block, right? But the 3 by 3 block which you have with E3 bar, E4 bar, and E5 bar can easily be seen to be one which can break up into a 2 by 2 block and a 1 by 1 block. So, although you do have a 3 by 3 block, it's really not an irreducible block. It can be reduced further. However, if you were using some other basis, it may not be obvious that this can be reduced further. Am I making sense here? Let me just give you a small example. Let's say somebody, some particular situation, you have this. This is what a particular linear transformation does to E1, E2, some two-dimensional vector space on which E1, E2 is acting. And so what you will get is a matrix which looks like this, nice and diagonal. It's obvious, if I were to borrow this language that we have used before, the two-dimensional vector space spanned by E1, E2 actually breaks up into two invariant subspaces, right? When you talk of the linear transformation L, you can't say that L is acting on the entire space, but you can equally well say L is acting on E1 on its own. So not only on E1, the space spanned by E1, that is a ray in the direction of E1, L is acting on that, and it will give you back a vector in that dimension only, in that direction only. Or L is acting on the space spanned by E2, and it will give you that only. So you can think of L's action on the space spanned by E1 and the space spanned by E2 as two separate actions. And basically, you can think of smaller, simpler spaces, one-dimensional spaces on which L acts. However, if instead of E1 and E2, you had used, say, F1, which is E1 plus E2, and F2, which is E1 minus E2, let's say, as your basis vectors, you can always do that, right? That is a legitimate change of basis. Would you agree?
Yes, sir.
Yes.
So what would F1 become under L? Well, simple. E1 will become 2E1. This is a linear transformation, right? So E1 plus E2 will become 2E1 minus E2. But this is neither F1 nor F2, right? That's actually twice E1 is actually F1 plus F2 minus F1 minus F2 by 2. So what you will end up with is F1 by 2 plus 3 by 2 F2. And if something similar will happen for F2. Of course, you could find this out by figuring out what the corresponding similarity transformation is, but a direct calculation is equally easy. But the point I'm trying to make is the matrix which will represent the same linear transformation, if we were to use the F1, F2 basis, will not look diagonal at all. It will not look reducible. It will look like this. Some other non-zero elements here. The point I'm trying to make is this form makes it obvious that L has a reducible action. It breaks up into two invariant subspaces. But that is obvious simply because you happen to choose the right basis right from the go. But if you had chosen F1, F2 instead to begin with, you would end up with a 2 by 2 matrix with non-zero elements everywhere. Then you would have to realize, okay, I can actually, instead of using F1 and F2, I can use some of the linear combinations as basis vectors, which will change this matrix into a diagonal one, which is, of course, the standard procedure which you carry out when you diagonalize a matrix, right? Here, what you're doing is something very similar. Your original 6 by 6 matrices may not look block diagonal at all, but you would have to try to go to a new transformed coordinate system, new set of basis vectors, such that they come as close to diagonal as possible. Diagonal is not possible, as we have tried to explain, because of the fact that diagonals would have meant they all commute, and they don't. The best you can do is block diagonal, and the underlying feature of doing this transformation is that basically you are looking at invariant subspaces which only transform among themselves when you do one of the symmetry operations. Okay? And then is this part clear to everybody? This is what we are going to actually learn how to do. That is how to tell what the sizes of the representations are first, then tell whether a given representation is reducible or irreducible. If it is reducible, how many irreps are in it? How many times? Maybe a single irrep may occur more than one times. So that kind of question, the tools for answering that kind of question is what we are going to develop in the rest of the, not the rest of the course, but in the next part of the course. Okay? But the moment you can do this, the advantage is that since K commutes with all of these RAs, being able to choose bases in which the RAs become block diagonal, all of them, RGs, all of the RGs become block diagonal, actually puts severe restrictions on the possible eigenvalues of K. It will turn out, in this problem, it will turn out, and we will again prove that later, that K actually will, sorry, just hold on. Hey, plus H. Plus H. Okay, I will call you back. Actor, okay, right. Okay. So basically it will turn out that K will act on E5 bar to give you E5 bar back. That's the consequence of K commuting with all of them. Which means E5 bar, E6 bar, they are guaranteed to be K eigenvectors. So if you know what E5 bar and E6 bar are, finding out the eigenvalues become trivial. It will also turn out that K actually, well, this is slightly non-trivial. So until I prove this, I'm not going to tell you why that's going to happen. But it will turn out that K will actually act on E1 bar. Okay, what would your guess be? If K were to act on E1 bar, what kind of vectors can you get as a result? Let's ask for your guess first. I've said K acting on E5 bar is E5 bar into something. So E5 bar is an eigenvector. So is E6 bar. What about E1 bar? When K acts on E1 bar.
A multiple of E2 bar and E1 bar. I don't.
You mean a linear combination of E1 bar and E2 bar? E2 bar,
sir.
right?
Yes, sir.
And K acting on E3 bar will be a linear combination of E3 bar and E4 bar. That's what you're saying.
Yes,
right?
Sir.
Actually, that's wrong. Okay, that's natural. That's a natural thing to think. So that is why I'm saying until we give a proof of this result, I'm not going to sort of try to explain why this happens because it's a bit non-trivial. But what will happen actually? Okay, in this case, let me also give you the answer, give you part of the answer. It so happens that this representation and this representation, although they're acting on different vectors, they turn out to be the same representation twice. That is, as I said, how many times does how many irreducible representations occur in a given reducible representation? That is a question, and also how many times. Here it so happens that these two irreps, actually they're the same irrep occurring twice. One, that is the same set of matrices basically. E1 bar, E2 bar get acted upon by a set of matrices. E3 bar, E4 bar gets acted upon by the same set of matrices. Okay.
So it's not 2, 3, 1. It's 2, 2, 1, 1. You mean? I mean, it's not 2, 3, 1. I mean, you mean the middle 3 by 3 block can be like
The middle 3 by 3
reduced
block
to
anyway is broken into. You can't have a 3 by 3
okay.
irrep for this
Okay.
particular group. Okay. If you're looking at the irreps only, this purple blocks. So I brought in this 3 by 3 block just to show you that there can be a representation here. But that representation is reducible, it can be broken down further. If instead of using E3 bar, E4 bar, E5 bar as they stand, you had used some combination of E3 bar with E5 bar as your basis, then this matrix would not look like block diagonalized, right? It will look like having non-zero elements here as well. But the point is I can always choose my basis in such a way that E3 bar, E4 bar will only mix among themselves, E5 bar will only mix among themselves. But it so happens that this representation, the one furnished by E1 bar, E2 bar, and the one furnished by E3 bar, E4 bar, these are the same representation repeated twice. That is to say, whatever RA does to E1 bar, E2 bar, RA does the same thing to E3 bar, E4 bar. And similarly, RB, RC, RD, and all that. So that's a statement at this point. Why does this representation occur twice, etc.? That's a result. That's a result which comes out of the calculation that we will learn how to do. Okay? But if a same representation is repeated more than once, then what happens is basically K will actually mix, K acting on E1 bar will actually mix E1 bar with E3 bar, the corresponding element in the identical irrep. And E2 bar will actually mix with E4 bar under K. Okay? So that's slightly non-trivial and non-intuitive. I understand that it's very sort of tempting to say E1 bar, E2 bar is invariant under K, but that's actually not necessarily true. Okay? This is a result. I'm not saying that I've explained to you why it is the way it is. It's a consequence of a theorem which you have studied in a special form in quantum mechanics. The theorem is called Wignericart Theorem. Remember, we talked about that last year, right?
Yes.
The general version of Wignericart Theorem used for general group representations essentially says this. We will talk about this definitely later on. But be that as it may, ultimately, do you realize what has happened? You were originally supposed to find out the eigenvectors and eigenvalues for K, which is you were supposed to diagonalize a 6 by 6 matrix, right? Now what has happened? You know already E5 bar is a K eigenvector, which means finding out the corresponding frequency is trivial. You just plug in, just make K act on E5 bar, whatever number comes out, that's your eigenfrequency, or actually eigenfrequency squared. Similarly, E6 bar is done. No calculation needed, almost no calculation needed. Well, E1 bar, E3 bar form an invariant subspace and form a subspace under K. E2 bar, E4 bar forms an invariant subspace under K. So what does that tell you? To find out the other 4 eigenfrequencies of K, what you have to do is solve 2 problems, but 2 by 2 problems. And not only that, it's not really 2 distinct 2 by 2 problems. Remember, I said that these are the same representations, right? That means the matrices sitting here and sitting here are identical. It will turn out that K will actually give you the same eigenfrequencies in both cases, identical. So if you solve that for E1 bar, E3 bar, E2 bar, E4 bar's problem does not have to be solved again. It's just the same. So, okay, let me just make it more concrete. If it so happens that E1 bar plus E2 bar is an eigenvector of K, then I'm not saying it is, but if it were to so happen that that is true, then E3 bar plus E4 bar will also be an eigenvector of K and will correspond to the same frequency as E1 bar plus E2 bar. So basically, the job becomes just solve one 2 by 2 eigenvalue problem, and the rest are trivial calculations. So what you should realize is that this is a huge simplification over what we were originally doing. Is this point clear?
Yes, sir.
Now, by the way, I'm not asking whether Y is E1 bar, E3 bar invariant under K clear or not. I definitely told you that I'm not going to explain that to you. Or why is it that the biggest irrep that you have here is two-dimensional? You will later find some very simple results. Okay, the results are so simple that I can just tell you that right now. One important result is the number of irreps that a particular group can have. It's pretty simple. It's just equal to the number of classes. That is why conjugacy classes are really that important. The number of conjugacy classes of a group is equal to the number of irreps of the group. That's one very important result. Again, a result which we will prove, but we definitely have not proven yet. Okay, so can anybody tell me how many irreps does S3 have? Three, right? Because you have three classes, right? So you know that irreps have three classes. This particular, sorry, S3 has three classes, and S3 therefore has three irreps. That, of course, will depend on the particular group you are talking about. For S3, you have three irreps. Okay. Also, another important result, which again I'm going to quote without proof right now, but which we will prove soon, is that if I take the dimensionalities of the irreps and add them all together, here we have three irreps, so their dimensionalities are just three numbers, D1, D2, D3. If you take the squares of the dimensionalities, add them together, you are going to get the order of the group. Okay, that's a result. I'm not proving this yet, but I will soon. So can anybody now tell me what D1, D2, D3 can be?
Here it is 2, 2, 2, 1.
2 to 1 is 4 plus 4 plus 1. That's 9.
1, 1, 2.
Yeah, it's
1, 1.
1, 1, 2.
Okay.
So actually, S3 actually has one two-dimensional irrep and two one-dimensional irreps. It cannot have a three-dimensional irrep. 3 square is already bigger than 6, right? So at least for small groups, actually, even this much is enough to tell you a lot about the possible irreps you can have. So when I wrote down this structure here, okay, I have drawn too many extra lines here. So let's try to get rid of some of them.
Sir, does this 112 have something to do with rotations, reflections, and the identity?
Not really. The it means it has two one dimension. Okay, it's not exactly no, in the sense that for this particular case, there are two one-dimensional representations. One of them is obvious, right? Remember,
Identity.
what is the representation? The representation has to be for every group element, you must have a matrix. And a one-dimensional matrix, of course, is just a number, a one-by-one matrix. Okay? And the important thing is the matrix has to obey this particular relationship. That is, any matrix which represents a group element must obey dg1 dg2 equals dg1 g2. Basically, this is nothing but a group action on a vector space. If you have listened to the last lecture, you would have understood exactly what I mean here, and you are supposed to already have done that. Now, if you are talking of this, basically in one dimension, what you mean is for every group element, there has to correspond a number, and when you multiply the numbers together, it has to reflect the group multiplication law. So one obvious representation is that you can map every number to every matrix element to 1. That's trivial, right? If dg is always 1 for all the g's, then dg1 dg2 equals dg1 g2. It's trivially correct because 1 times 1 is always 1. Okay. Remember, being a representation doesn't mean each of the DGs have to be different from each other. It just means that for every G, you need a matrix, and the matrices have to obey this particular multiplication rule. That's it. So one-dimensional representation every group has, which is every element is represented by the number 1. And that works. Okay. But other than that, there is one more representation, 2 one-dimensional representations, right? So we had these 6 elements. The 1D representation that we were talking about, these are represented by, all of them are represented by 1. Okay. But there is another 1D representation apart from this one, another irreducible 1D representation, which is different from this one. Can anybody guess what that is going to be? And there, the physical identity or the geometrical identity of these operations, whether they are rotations or reflections, actually make a huge difference. That will help you to figure out what the representation is. Okay, let me just ask you one thing. If you were to multiply 2 rotations, that is, do one rotation after the other, what do you get? A rotation or a reflection?
A rotation.
You do 2 rotations, one after the other, you get a rotation. You do 2 reflections, one after the other, what do you get?
Rotation by pi. No, 2 reflections, identity.
2 reflections, you always get the identity? I'm not saying the same reflection.
2 reflections give a
Okay.
rotation.
Ha.
2 reflections give a rotation.
Yeah, even the identity is a rotation, by the way.
Yes, sir.
2 reflections always give you a rotation. And a rotation and a reflection gives you what? A reflection. Good, a reflection. So can this help you to figure? So, okay, let me just make a sort of table out of this. Rotation, reflection, rotation, reflection. 2 rotations, rotation. 2 reflections, rotation. Reflection, rotation. So did I write it like, okay. 2 reflections is a rotation. A reflection and rotation is a deflection. Rotation and reflection in that order is also a reflection. Now, does this table remind you of something?
Z2.
Yeah, this is exactly the same thing as Z2. And Z2 has elements which are 0 and 1 if it's addition modulo 1. But here we are talking about multiplication. And there is a multiplicative group with 2 elements, right? Where the operation is actually multiplication of numbers. What are those numbers?
1 and minus 1.
1 and minus 1, exactly. In fact, the representation that you have, the other 1D representation is simply identity. All the rotations get represented by 1. All the reflections get represented by minus 1. So this is one 1D representation. Okay, why this is called chi, we are going to come to later. This is another 1D representation. Okay. And the result that I was also quoting, I didn't prove that, but I am quoting here, is that for the molecular vibration case, it will turn out that the 6x6 matrices that you have are reducible. Of course, they have to be, because we have already figured out that the irreps, there are only 3 irreps, 2 1D and 1 2D. A 6D rotation has to be reducible, right? But you can also figure out not only that it is reducible, you can also figure out what its reduction is. In other words, you can figure out that the 2 1D representations occur once in this representation, and the 1 2D irrep will occur twice, which is why I have these 2 blocks, and which is why I'm so confident when I say E1, E2 actually mix among each other in exactly the same way as E3, E4 mix among each other, because that's what group theoretical calculations would have told me, that the 2D irrep is occurring twice here. Okay, again, I'm of course assuming a lot of results, which we will see how to prove. But I'm trying to give you the motivation as to why you would like have to learn about these techniques. Once you know those techniques, these results, that this will break up into 2 by 2. 2 of 2, 2 by 2s of the same kind, etc., will become sort of obvious. And the upshot of it, at least for this particular problem, would mean that instead of solving a 6 by 6 matrix equation, you will essentially end up solving only one 2 by 2 matrix equation, and that's it. By the way, you have already seen an extreme example of this in action in a particular system, where you had where you had 3 times a huge number of degrees of freedom in the system. But you ultimately, when you solve for the vibrations, you end up solving only for a 3-dimensional vibration problem, basically, a 3 by 3 matrix. I'm pretty sure you have already done that, but maybe you have not seen that in this language. A system which has so many symmetries that it can reduce 3 times capital N degrees of freedom to, and so 3n by 3n matrices can be reduced down to basically one 3-dimensional matrix calculation. Can you guess what I'm talking about? Where n is of the order of Avogadro number. Let's.
KTG.
What is that?
Kinetic theory of gases. Kinetic theory of gases.
Kinetic theory of gases, no.
So Euler angle.
The Euler angle is basically not 3n, right? There's a rigid body rotating. That's rotation only has 3 degrees of freedom. You have 3 translational and 3 rotational degrees of freedom. I'm saying 3 capital N, where capital N is huge, maybe Avogadro number or more. That order. That should be a dead giveaway. So kinetic theory of gases, maybe, I guess you were guessing in terms of the Avogadro number, but you need some symmetries of the system in such a way that this will reduce the problem down to just doing a 3 by 3 matrix calculation, diagonalization. Are we talking about what?
Body motion.
Rigid body motion is, well, rigid body motion has only 6 degrees of freedom. There we don't have symmetries. There we have so many constraints that we have frozen the thing out completely. Okay, I'm sure you have all done this problem. Maybe you have not used this language. Condensed matter physics, right? But where in condensed matter physics? Look, the moment I say Avogadro number, where does it get used? Essentially in condensed matter physics. But why? Okay, I actually gave up the answer. Once I told you condensed matter physics and a vibration problem.
Phonons.
Phonons, yes, but that's the second step. It's really the theory of lattice vibrations. When you found out the dispersion relation, I'm sure you have done the dispersion relation calculation, right?
Yes, sir.
At least forget the more complicated case, even for the 1D chain. How many atoms were involved? How many atoms were there in the chain? Well, that's a rhetorical question. I'm not asking exactly how many, but you said they started with capital N atoms, right? Capital N could be a huge number. But ultimately you ended up solving only a 1-by-1 equation to find out the dispersion relation. Why? Because you had this translation symmetry in the system which actually helped reduce the problem to a small problem. For the 3D lattice vibrations, which I'm not sure whether you have done in your class, basically what will happen is 3n degrees of freedom, fine, but they essentially end up giving you 3 distinct modes, which you can get by solving a 3 by 3 matrix equation. And that is the power of symmetry. That's the power of the translational symmetry which this crystal lattice has. And that's the kind of calculation that we will learn to do sort of as a matter of routine. Okay, so hopefully this was the advertisement part. I was trying to advertise why you would want to learn about group representations. I've of course not proven most of the results that I've talked about here. The proofs will come in the coming lectures. But the point I try to make is you have a reasonably complicated problem which can be made a lot simpler by using these group theoretical techniques which hinge on representation theory. Well, a triangular molecule is simple, but suppose you had a complicated, say, fullerene molecule, C60, vibrating in 3 dimensions, 180 degrees of freedom. The calculation can be cut down to a very small final calculation because of the immense symmetry it has. Okay. Any other questions? Any questions on this? Okay, if there's none, somebody was asking about Poincaré transformations.
Yes, sir.
Go ahead.
Sir, I mean, in the lecture, you first defined the Poincaré group, and then you came to semi-direct product. So,
Yeah.
I mean, when you define the semi-direct product, you consider the, I mean, you wrote G and curly G or script G. So, I
Yeah.
mean, where G was the set, and you consider this curly G to be a subset, a subgroup of the group of automorphisms.
Or isomorphic to a subgroup of, well,
Yes,
not order or G. If we could say something like, say, let's call it gamma, which is a subgroup of odd G. Yeah.
yes, sir. So, and then you go on to say that this Poincaré group is a semi-direct product of this group of translations and this Lorentz group.
Yeah.
So, I mean, I don't know. In hindsight, when you tried to write the group action, you denoted it by this lambda 1 a1. Okay, I mean lambda comma a meaning.
Right.
So I don't. I mean, because this I suppose this a is for the translation part, and this
Yeah. So lambda A is just a label for x going to x prime, where x prime is lambda x plus A. So this is the translation, as you rightly point out. And this is the Lorentz transformation which acts on the 4 vector x.
yes, sir. So I don't know, but I mean, it makes more sense if we label it by a lambda, because I mean, this
by
lambda.
yeah, of course,
Yes,
if you were doing this strictly group theoretically, that is, if you had learned about Poincaré transformations first from group theory and never before, then I'm sure to make it consistent with the group, that's what I kept on saying several times, that the semi-direct product structure, when you write G comma curly G, there you have G alpha. But
yes, sir.
and here you have lambda A, where things are sort of swapped.
Yes, sir. That was my point.
Yeah, they are. Well, the point is, Poincaré transformations have been around with us from before group theory became a big thing in physics. Okay?
Yes.
So, basically, the standard notation of a Poincaré transformation as lambda A is ingrained in physicists' minds. You cannot simply change it today. Okay?
Yes,
Well, if you try telling that to a standard physicist, he would just go back and say, why don't you ask the mathematicians to change their notation and write curly G first and G next in the semi-direct product? After all, it's a rule, right?
yes, sir.
That is, when you write the semi-direct product, that you write capital G first and alpha, the curly G part next. Somebody might even say that because this is what happens, say, alpha is the thing which sort of does its own thing. Why don't you keep alpha more important than put it first? Now, if you think of it in physical terms, translations are a lot more trivial, at least in the richness of the results it gives you, compared to Lorentz transformations, right? If somebody asks you, what is more important in the Poincaré transformation, the Lorentz transformation part or translation part? That's an unfair question because both of them are important, but I'm pretty sure everybody would vote for Lorentz transformations, right? As something which is physically more important.
Yes.
So I'm pretty sure physicists would never write Lorentz transformations as A comma lambda, because to them lambda is the sort of jewel in the crown. A is sort of something which is just coming in for the ride. But you're perfectly right. If you wanted to make this completely consistent with the standard notation which is there in mathematics of the semi-direct product, you would actually write them in reverse order. Look, I did not write down the Lorentz-Poincare transformation to motivate the notation for semi-direct products, but the notion of semi-direct products. The two are different. Direct products are easy enough to understand, okay? But if you look at the semi-direct product, you might immediately have a question as to why would you think about something so complicated? This rule, GG prime alpha alpha prime, the direct product rule, is sort of the most natural thing you can think about. What else would you think? But this fact that G, here alpha gets to act on G prime and that combines with G, that sounds a bit perverse. So unless you have some motivation for studying some structures, you would usually not do that. In physics, it so happens we do have a lot of motivation for studying such structures. Mathematicians have other motivations. For example, just like knowing the direct product structure actually tells you a lot about the group, including a lot about its representations. Even knowing that a group is a semi-direct product of smaller entities actually can help you say a lot about the representations of the group. So that would be a mathematical sort of motivation for this particular definition. But in physics, we have very important groups which actually does have this, and it's sort of easy to understand why. Because whether you do a translation before you do the Lorentz or after you do the Lorentz actually makes a difference, right? That is, if you go from x to, first go from x to x plus a and then do a lambda, that will give you lambda times x plus a. On the other hand, if you first did a lambda, you get lambda x, and then you translate it, you get lambda x plus a. These two are, of course, different, right? And that is part of the reason why the semi-direct product rule for Poincare is more complicated than each doing its own thing. And can anybody guess any other important physical group where this kind of semi-direct product structure will arise? It's a group which is one whose name you definitely have heard, even if you have not heard anything else of group theory. There's another group, just like the Poincare group, is the translation group's semi-direct product with the Lorentz group. There is another very important group in group theory, in physics. There are more actually, but another very, very important group in physics, which you have definitely heard of, where you've heard it being called a group, which has this semi-direct product structure. Okay, how many groups have you heard of outside this group theory course in physics? Rotation group you have heard of, right? Other than that? There are at least two more groups that you definitely have heard of in a physics course. They have been referred to as groups. Lorentz group, rotation group, let's leave them out. Apart from that.
SU.
I
don't know, SU or U.
SU, well, that depends on what kind of courses you have done so far. You may not heard of them. I'm saying outside this particular course. There's at least one pair of group which is mentioned by name in a course which I've already done. And there it definitely was mentioned by name, although maybe group theory was not really used there. So what are operations which keep a particular point fixed called?
Isometries.
No, isometries are operations which keep lengths fixed and distance between points fixed. I'm saying what is an operation which keeps a particular point fixed. They're all isometries, but specifically keeps a particular point fixed. Translation, for example, is an isometry. But that's not in this group.
The rotation about that point will keep that point fixed.
Apart from that, anything else? Rotation is fine. Anything else?
So point group symmetries in crystal.
Well, yeah, that was a thing I was driving at. You must have heard of the term point group, right? In solid state physics? Symmetries, or the group of symmetries which keeps a particular point in a crystal fixed. They are typically rotations and reflections. Reflections in a plane which contains that point. But they are, whether they are rotations and reflections or whatever else, the point is they keep a point fixed. Hello? Yes? Sorry, I'm busy right now. So apart from point group, what else have you heard? Another group in condensed matter?
Space group.
Yeah. And what's a space group? Space group basically is a collection of all symmetries of a Bravais lattice, which is point group operations which leave the Bravais lattice fixed while keeping one point fixed. And space group essentially can move the entire lattice. There is translations also included. And space group actually is the semi-direct product of the translations, lattice translation, not every translation, and the point group. So condensed matter physics uses semi-direct product in a big way because all the symmetry considerations there. Why do you have so many space groups? What kind of point groups can you have? All of this essentially hinges upon this semi-direct product structure. And because it's a semi-direct product, you have I'm pretty sure you've heard of special things like glide planes, for example. Operations which cannot be described either like a point group operation or a translation, but a combination of the two, non-trivial combination of the two. Such things exist because this is a semi-direct product where one gets to act on another. I'm sure everybody has heard these names, right? Space group and point group. Yes? No? What? The point is, these are group theoretical things, and space group actually is a semi-direct product in exactly the same way the Poincare group is. A point group operation basically would be either rotation or a reflection. A space group operation would be a lattice translation. And when you put them together, translation is just a lattice, not all translations, but just translation by Bravais lattice vectors. And when you put them together, you get a space group operation. And the combination rule is exactly like the Poincare group's combination rule for the very same reason. Under capital R vector, a point X goes to capital R acting on X plus R vector. And that gives rise to the Poincare group-like structure for combinations. Essentially same kind of mathematics. Okay, any further questions? Okay, if not, then let me ask you another question, which is a bit less trivial than the things we have been talking about so far. I don't need a recording of that part anyway, but